Mercury 2 oxide breaks down or decomposes readily when heated. If we were to weigh the compound before heating and compare its mass to that of the mercury remaining after the reaction, it would seem that decomposition causes a change in the system's mass. The product mercury would weigh less than the reactant. In reality, the decomposition liberates the reactant's oxygen atoms as gaseous dioxygen O2. All matter present before the reaction still exists after it. The reaction obeys the law of conservation of matter.
In the old days, people would measure so much mercury 2 oxide, which is the formula HGO. They'd weigh it before they heated it up, and then they'd heat it up like the little video shows right there. And the mass of what was left was less than the mass that they started with. And that's why people didn't really understand how this was all working out. But now what we do is we realize that all the matter that goes into a reaction has to be accounted for on the way back out. So in that example with the mercury 2 oxide being heated, the O2 oxygen is liberated. That's those little red, double red dots there going away. And the mercury, kind of the silvery thing, is what's left. So no mass was lost in the reaction, but we did transform it. And that's usually what chemistry is all about. So the same numbers of atoms are present in a reaction at both the beginning and the end, all right? The amount of the matter in the system does not change, all right? I like to think about this as you have to put on your accounting hat. You have to take into account the matter that was there at the beginning and the matter that was there at the end. They will rearrange on you, but you won't gain or lose any, and that's important. The fancy way to state this is through what's called the law of conservation of matter, and that just says that matter cannot be created or destroyed. All the matter that goes in equals all the matter that goes out. Informally, it's also known as the law of mass action, and both terms mean the same thing, all right? So again, all those both say is that you have to account for all the matter. You can't lose matter, you can't make more matter and stuff like that, and that's going to lead us to what's important in this chapter, which is being able to balance a chemical equation. Balancing chemical equations or chemical reactions is just the way that chemists know that all the matter is taken care of. We know where the matter went to, we know where it's coming from. Very important in chemistry. Lavoisier was the one who proposed this idea where matter has to be conserved. And conserved here just means you're not creating or destroying anything. And Lavoisier was a really cool chemist. He was politically on the wrong side of some things. So anyway, I'll let you read up on that later if you're interested. But Lavoisier was cool. He was a French chemist and stuff. And again, note the date, 1788. Pretty crazy. So anyway, Lavoisier basically just said that, yeah, matter that goes in must be accounted for on the way back out. You can't create matter or destroy matter.
When pieces of aluminum foil are placed in a beaker containing bromine, a violent reaction occurs. The elements react to produce aluminum bromide, which consists of 2 aluminum atoms for every 6 bromine atoms. It is visible as a white powder deposited on the beaker.
So in this reaction, you are making aluminum bromide. Now, aluminum bromide, all right, is really AlBr3. That's what we would have done before. But because aluminum is in group 3A, one of my twisted metals, a lot of times aluminum likes to make what I call a dimer, which is basically one aluminum bromide and a second aluminum bromide coming together. And that's what we have right here. The Al2Br6 is an example of 2 AlBr3s coming together. And this is a function of this twisted metal process. And we're going to talk more about why group 3A is so twisted. That sounds kind of funky. Anyway, and please realize that twisted metals is just my informal way of talking about that group. But anyway, this is an example of how this works out. But anyway, neither here nor there. So let's say we want to make this Al2Br6 dimeric aluminum bromide blah 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 compound. All right, right, cool. Well, we could just throw random amounts of aluminum and bromine in and make, hopefully, the Al2Br6. But if you put your thinking helmet on, all right, we can do a better job. The formula for this thing is Al2Br6. So if we're going to make one aluminum bromide dimer, one Al2Br6, we're going to need 2 aluminums, and we're going to need a total of 6 Br2s, or Brs, 6 bromine atoms. And if you look on the bottom down there, we've got some aluminum atoms. Those are those kind of gold atoms right there. And then there's also over here some Br2s. And on the right-hand side, here's this big Al2Br6. And if you see there on both the right and the left side, there's 2 gold aluminum atoms. And there's also a total of 6 bromine atoms. On the left reactant side, there is bromine Br2. On the right side, they're all connected to the Al2Br6. But the important part here is not the form it takes, it's just that the atoms going in are equal to the atoms going out. And that's what we've got. 2 gold on the left, 2 gold aluminum on the right, and a total of 6 bromine atoms on the left, 3 Br2s, and a total of 6 bromine atoms on the right in that Al2Br6. So to write this as a balanced equation, what we would do is we would write a 2 in front of the Al, we'd write a 3 in front of the Br2, and we would have the invisible 1 in front of the Al2Br6. That would be the way that we would get across 2 gold aluminum atoms, 3 Br2s, or 6 bromine atoms total to make that Al2Br6. So this is an example of how you balance an equation, all right? You want to make sure that the atoms are the same on the left and the right. And one thing that I do sometimes when I get stuck, I literally write a line down the middle between the reactants and products. And you can see how you have 2 aluminums on the left, and you have 2 gold aluminums on the right. And you have a total of 6 bromine atoms on the left, and you have a total of 6 bromine atoms on the right. And if both sides are equal, that means you have a balanced reaction. And honestly, this kind of way of balancing on both sides is totally cool. I highly recommend it if you ever get stuck on these.
In the combustion of propane, a single propane molecule reacts with 5 molecules of O2 to produce 3 molecules of carbon dioxide and 4 molecules of water.
Propane is used in a lot of home barbecue systems. So if you've ever had a propane barbecue and stuff going, then you're good to go. Propane is a compound with carbon and hydrogen. And we're going to see in the next section that propane, like a lot of the organic things, reacts with O2 oxygen to make CO2, which is what we have on the left side, and water, H2O, on the right side. Oxygen is the red atom. So notice on the CO2, the oxygens are on the left and the right, and the blackish carbon is in the middle. So that's CO2. On the right, water oxygen is in the middle, and the hydrogens are one kind of to the lower left, and one kind of to the lower right. We'll talk about why those look that way in Chem 222. But for right now, let's imagine that we wish to balance this reaction. Now, propane is C3H8, oxygen is O2, CO2, carbon dioxide, and water are the products. So the question is, how many of each do you do? And what I would do here is I would start by balancing the carbon and hydrogen first, because all of the carbon in C3H8 ends up as carbon in CO2, just like all the hydrogen in propane ends up as water. And I'm going to leave oxygen for last, because if I change the number in front of oxygen, it will only affect the O. You're going to have oxygen from 2 sources, CO2 and water from there. So let's go ahead and try this. C3H8, the 3 of carbon, let's put a 3 right there. That would give 3 carbons on the product side, just like we have 3 carbons on the reactant side. And 8 hydrogens in propane. Now water comes as H2O, so 2 hydrogens for that. So let's tentatively put a 4 right there. If you do that, now the carbons and hydrogens are good, but the oxygens aren't right. And if you're ever uncertain, go ahead and do the balance thing. Here's carbon, hydrogen, and oxygen. So right now we have 3 carbons from propane, and we have 3 carbons from CO2. We have 8 hydrogens from the C3H8, and we have 4 times 2, 8 hydrogens from the water. Now, oxygen, though, is tricky because you can see it's in both CO2 and water. So on the product side, 3 times 2 oxygens for CO2 means 6 O's. But I also have 4 times 1. We also have 4 oxygens from the water. So that means we have a total of 10 oxygens on the product side. And the reactant side, O2, we have to have them in 2. So tentatively, let's put a 5 right there. Because if we put a 5, then 5 times 2 is 10. So knowing that, I would have an invisible 1 by the C3H8, a 5 by the O2, and that would make 3 CO2 and 4 water. And I think that one is good to go. So let's check it now. Bam, 5O2 makes 3 CO2 plus 4 waters. But again, notice there how I balanced it. I made like a little chart. You can make it in the middle of the reactant product arrow, or you can do it on the side, whatever works. This is a good way to check yourself if you're ever stuck. This is another example of a compound that reacts like the C3H8. This particular one is called diboring. You don't need to worry about that. But anyway, B4H10 also reacts with O2. It makes B2O3 and water. So again, what I'm going to do on this one, let's make a little chart. And I'm going to have boron, I'm going to have hydrogen, and I'm going to have oxygen. Those are the atoms on both the left and the right. And right now we have 4 borons, all right, atoms in the B4H10. So that means at the very least, I'm going to have to put a 2 right there, because 2 times the B2 would give me 4 borons, and they would be balanced. So tentatively, let's put that there. But we also have 10 hydrogens, all right, from the B4H10. So let's put a 10 right there. Now, on the water side, you can see that hydrogen once again comes in pairs of 2. So let's put a 5 right there, and that would make everything balanced for hydrogen. And like before, we'll do oxygen last. So oxygen comes in 2s, and you can see you have 2 times 3, or 6 oxygens from the B2O3. Plus 5 times 1, 5 oxygens in the water. And maybe you can see this is going to be a little bit of a problem because we want 11 oxygen atoms, but on the reactant side, oxygen comes in 2s, all right? So you can't really have 11 oxygen atoms if they come in pairs of 2. What we would like to do is put 11 halves right there, because 11 halves times 2 would give us the 11 atoms we need. So if we could put 11 halves right there, this would be balanced because it's 11 halves times 2. The 2's would cancel out. We have 11 atoms on both sides. Oh, cool for school. And we'd have 1 B4H10 plus 11 halves O2 going to 2 B2O3s and 5 waters. But chemists really hate fractions, all right? If you don't have to have a fraction in chemistry, you should try and avoid it. It's just kind of the unwritten rule of chemistry. So we can't leave this as 11 halves, all right? That's just like bad news when it comes to chemistry. But don't despair, because it's easy to get rid of something over 2. You just multiply by 2. If you do that, though, if you multiply by 2, you've got to multiply everything through by 2. So instead of 1, 11 halves, 2, and 5, we're going to multiply all those numbers by 2. You're going to have 2 B4H10, and if you multiply this by 2, it becomes 11 O2. we would then have 4 B2O3s, and we would have 10 waters. So let's make a prediction here. 2, 11 on the reactant side, and 4 and 10 on the product side. And if you do this, bam, 2 B4H10 plus 11O2 makes 4 B2O3 plus 10 H2O. So you can see the kind of process that's used to balance an equation. The diagram below shows the reaction of phosphorus and chlorine to make phosphorus trichloride, and it says which one is correct. Now remember here and stuff that phosphorus comes as a tetramer, all right? It's not just one phosphorus atom, it's a whole bunch. So if you look at these, the reaction involves 1 phosphorus atom and 6 chlorine atoms to produce 1 phosphorus trichloride molecule. That's not right. Down here in the very picture, you can see there's 4 phosphorus, 4 gray P's, and we do have 6 Cl2s, so that part would be right. Actually, it's not right. 6 Cl atoms, it's 6 Cl2s. It's not 6 Cl, so that's not right at all. That whole thing is bogus. Just drop that one like a hot potato. Next one. Reaction involves 4 phosphorus atoms. All right, that's right. It says P4, but it is 4 phosphorus, and 12 chlorine atoms. So 6 chlorine Cl2s times 2 would be 12. To produce 4 PCl3 molecules. Hey, I'm kind of liking the sound of that one. So yep, that one is correct. That would be the best answer. And again, it's because, as you can see there, phosphorus isn't an individual. It's one of those weird tetramers. It makes then 4 PCl3s. The last one, again, doesn't have the 1 P atom, so that one's kind of messed up as well. So when you're balancing equations, here's some hints and stuff to help you around. First of all, balance the atoms which occur in only one compound on each side last. And that's an example of the oxygen we saw. O2 was by itself and stuff, so that's why that was the last one to do. Do the more complicated, if you will, combinations first and do that last. Balance the remaining atoms first and stuff, totally. You want to reduce the coefficients to the smallest whole numbers, and this is important. Let's say that you had something like, it would be 4 Na and 2 Cl2s making 4 NaCl. Let me write that out. We could have 4 Na and 2 Cl2s making 4 NaCl. And technically this would be balanced, all right? The atoms on the left equal the atoms on the right, 4 Nas on both sides, 2 times 2, 4 chlorines on the left and 4 chlorines on the right. However, reducing coefficients just means make them all the smallest whole numbers possible. So as an example of that, 4, 2, and 4, we can definitely divide all of those coefficients by 2. And we'd have a 2 right there. 2 divided by 2 would be 1, invisible, and this one would reduce to 2. So you want to make the coefficients as smallest whole numbers as possible, and that's really important. Most of the time, it's not a big deal, but once in a while, it does happen. Try and make it bad. Now, if you ever have a reaction and you're not certain if it's balanced, check yourself. Do that kind of analysis where you look at the atoms on both the reactant and the product side, and if the atoms add up to both sides, you're good to go. You can always do that, and I do that myself sometimes. And finally, all of the charges will be balanced in a chemical reaction as well. And this is something that we'll talk about in a future lecture. If you look at the sodium and chlorine making sodium chloride, all of those are neutral. They don't have a charge. And if you had like an Na plus on the left and nothing with a charge on the right, that would be an unbalanced reaction. So it's really mass, the atoms, and the charges which are balanced. And we'll focus more on the charges in a later lecture. But if you have that and stuff, it will make you stronger overall, which is cool.